I'm going to look at what if.
I was supposed to do something right. I'll throw it too. Oh, wow.
Anything important to discuss in ModPhys today, do we?
He said he's going to go over material and something about a new project.
New project?
Yeah, that's what I'm going to die. I'm going to jump over all of Act 2.
Did you forget to...
I didn't forget. I didn't have time. I was studying for the ModPhys.
Did it help you? And then you're studying affect your grade.
I blinked. I couldn't think.
Wow. Anyway. Hey, Micah. How badly did you fail?
How badly did I what?
Fail.
I've answered every question.
What?
I answered every question. That's all I'm going to say.
I need to ask. Do you know the question I asked about how many ways to hit him per second? What did you get for an answer?
25.
Wait,
That's what I'm...
Yes! Yes! Okay.
Not exactly. I got 25 over something.
So I did it using the energy because you can't use the momentum. It's impossible because it's C. So I'm like, okay, screw it. I'm doing it with energy. It's probably incorrect, but...
what is...
I did it by using the ratio between the number that he needs and the number
What did you get with the little butterfly thingy? It's flying. You have the two people throwing things at it. What did you get for that?
Wait, I don't remember that.
What?
I don't remember that.
Pokeball.
Yeah, you have the two Pokeballs, and then you have the one person that's flying next to him.
Missy?
I got
Yeah.
C. I got C.
Okay.
I calculated like 8 times, and every time I got C.
See, here's the thing though. I'm like, okay, screw it. This isn't the way he wants me to answer it. I'm going to have it flying directly at the explosion.
Knowing him, it's probably the correct answer.
It's technically a correct answer.
What was the answer you got?
So I said the velocity does not matter as long as it's flying towards the thing. As long as it's flying parallel and in between in the middle of the two things, the velocity does not matter.
So how's that test?
I want to die.
It's technically true.
Yeah, she's dead.
She did anyway, flying at relativistic speeds. You know this to be true.
I actually wrote that. I think I wrote that. I remember.
I did write that. I did write that.
That's the Wix rod.
Quarter grades. I take no attention to quarter grades. No one in science does. Like that's like a math thing for some reason.
Do all scientists have quarter grades?
The science teachers, we just don't do it. They don't. I don't even care. Like we just the quarter doesn't do anything.
The quarter does do something.
But there's a few. But I know there's a few like scholarship applications or something that look at first quarter grades. If there's one of those and your grade is at a place that you can make an argument about it, come talk to me. I don't care about your first quarter grade. And if it'll help you, I'm not going to like just arbitrarily change it. If you can make a case for having something different on your quarter grade, I can listen. You know, because I don't care about the quarter grade. No one cares about the quarter grade, except for this tiny number of like scholarship applications. In which case, you know, I'm happy to give you more money. You know, I mean, I'm happy to give you my money. Okay, so I'm going to tell you a quick story. One of my old students, Tasha Aronitis, class of like 2011 or something. She was a really good student. She had her in ModPhys. She went to college at Harvey Mudd. If you've heard of Harvey Mudd, it's basically MC University. It's a lot. It's very IMSA-like. But it's in California, warm and sunny. That part's different. Also, the building's much nicer. So Tasha went there for it's a tech school. It's a math science school. Tasha went there for college, really loved it. So she went there, and the first, everyone's required to take freshman physics the first semester, and their first semester of physics is on relativity. They do that, I think, just to kind of be different, because they like being different. And so they like want us to, rather than start off with boring mechanics like everyone else does, it's like let's start off with something fun. So they start off with plus. I think it's semester quarter, or they do it on relativity. So she went in there and said, do you have a placement test for that? And they're like, well, we don't have a placement test for relativity because no one's taken relativity in high school, or at least not at any decent level. And Tasha, who had done very well in ModPhys, was like, well, actually I have, like, is there something you can do? They said, well, you can take last year's final. She's like, okay. So they give her last year's final. And so she sent me an email after that, and she sent me an email. She said, hey, Dr. Dong, I just took the displacement test. She's like, I always believed it was way easier than your relativity exam. So the point is that if you found this exam difficult, well then, you're ready for college. Right?
I want to die.
You're ready for college, Eden?
Yeah, there's the point is, if you found the exam difficult, well, that's okay. I mean, other people found it difficult too. And that's fine. I have not graded them yet.
Oh.
I don't want to look at it.
Please
I could have never guessed.
Because of the timing of everything, especially with the short day, I decided let's not start the project today. I think it was too disruptive. Instead, I'll just do a short lesson. We'll have a short, real easy homework. I like this next unit. I always like this.
It's part of interaction.
We know that it's all wrong.
Yeah.
Stop using it.
Oh, I know what we're doing.
Every time, Benji.
What are you doing there?
Not hard. I see Dr. Buck's handwriting.
Hey, can you flip it? Can you flip it?
This is going hard.
Yes.
I bet you I can have this water bottle upside down.
Yes.
I think this unit is a lot of fun. You don't have to, it's up to you, but it's definitely a switch from relativity. Hey, not to everyone.
Actually, you could flip it without any water flowing out with the bottle flip. Be extremely difficult, though.
The amount of math, and particularly the amount of algebra you have to do, backs off substantially. Okay. Zero full on quantum mechanics, of course, there's tons of algebra and calculus and stuff in it, but the basic stuff that we're doing is much less. So the amount of algebra is much less than you do than you have to deal with in the relativity section. So those of you who kept getting annoyed by all the algebra, like you're luck, quantum mechanics is much less. And the way we do the part relativity. Okay, so let me show you what's going to be your new best friend for this next sort of subunit. You know, the next bit, which won't be for a while because I'm going to insert the next project in between. Okay, and there's a little up here at the top, here's that, and I'll observe some atomic particles. Okay, and if you open it up, you will see a list, a 3-page document listing subatomic particles. First of all, do not attempt to memorize this. That would be ridiculous. I will either give you the relevant information, or in most cases, just give you the whole thing for any test where you would need. So, but it gives you these are the fundamental fermions here. It gives you flavor and charge and mass. The flavor we'll talk about in a moment. Gives you the bosons. These are, this first page is the fundamental particles. That's it, these are the ones that we think are not made up of other things. And then the next 2 pages are the composite particles. Here's and there's a partial list. I just listed the most common ones. Here's a list of baryons. What are baryons? There's a bunch of them. You have to learn some Greek. You don't really learn some Greek. You need to learn some Greek letters. It's not so bad. And over here is a list of mesons. Okay, so these are the particles that we're going to be dealing with. I recommend that that you just print this out because it's really a lot easier for doing. Because we're going to use it for several homework assignments, and it's a lot easier to have it in paper than to have to keep on going to it online. I recommend just printing it out. I think it's easier. It's 3 pages you can handle. Your printing quota can handle that, right? Okay, so those are the subatomic particles, and then we'll start talking about what these things mean and so forth. But we are going to enter a little unit on particle physics. I kind of insert this. It's sort of like it goes with the quantum mechanics unit, like from the big exam and stuff. But I kind of insert this here now so we can help us understand things related to the project, things related to the Fermi lab trip, et cetera, et cetera. Just give us a basic idea of some simple particle physics. So the main thing of particle physics is that it's all about particle interactions, right? I mean, if you think about it, that's really all physics is interactions between things, right? And so the interactions between particles are what we're looking at. And so you will have interactions that they will look like things like you might have an interaction that looks looks like this, for example. Okay, and this tells you that you are that you have an interaction of this particle and this particle. They interact, and the result is this particle and this particle. Okay. In fact, it should remind you an awful lot of something else. Right. Right.
I got it.
There's a lot of things you compare with chemical reactions. So what you do, kind of like chemistry, is you look at this particle and you're like, okay, what is this particle? Then you look over there. I mean, you look over on the sheet and you see, where is that particle? Well, it's up there. It's actually up on this page. There's, well, both of them actually.
Well, some stuff positrons and muon and such.
But over here it says electron parentheses E. And like, and then there's muon parentheses mu. That's Greek letter mu. And we're like, okay. So those things are available. So you can look them up and find all their properties right there. Okay. So I need to give you one note, which is every particle. Yeah, well, yes. Every particle has an antiparticle. Okay? I don't list the antiparticles on there. But it has the same mass, but opposite charge. Okay? So antiparticle has the same mass but opposite charge. There's nothing weird or freaky about antimatter. It is not unnatural. It is not bizarre things that are not of this earth. It does not form rifts in the space-time continuum. It is just another particle. Okay? There's nothing strange about it. We've known about it for a long time. Has anyone read that horrible book, Angels and Demons, by Dan Brown? Sorry if you liked it. It makes the most absurd statements about actually a lot of things in physics, and from what I understand, art history as well. But it makes a series of extremely absurd statements. But one of them is this big deal they make about antimatter being a bizarre thing that is not of this world, proof of the existence of God. Kind of like, what on earth are you talking about? Anyway, the point is that's all dumb. Antimatter is just particles. Okay. The main thing is we don't see any on Earth. On Earth, we're all made of matter, which is just as well when you see how they interact with matter. But these things, they could exist elsewhere. They can exist elsewhere. They exist just fine. They follow all the same laws basically, but they have equal mass and opposite charge. Yeah.
What about particles with no charge?
Particles with no charge still have antiparticles. But you're like, but they have the same charge. Yeah. But they're still antiparticles. Like, what's different about them? We'll get there. Okay. Well, we'll get to some of that today. Okay, so, what's the class on 55? Yeah, right? Okay, there's a little sign that we write up for these particles. What do you suppose that minus or plus sign represents?
Charge.
The charge of the particle. Good. So, here's how you figure out. So, I don't put any of the antiparticles on the list. You have to add them yourself. It's not hard. This, for example, E minus, is a negatively charged particle named E, which is the electron. Good. So E minus is the electron. The antiparticle of it is written E plus. Okay? And that is called the positron. Now, the positron was the first one discovered, and when they first discovered, they didn't know what it was. It's like an electron, but it's positive, so they call it the positron. Once they figured out what antimatter was, everything else is actually named very consistently. Because, important rule, starting in 1960, before 1960, the names of things that this has come up with are good. After 1960, they're stupid. They get progressively stupider as time goes on.
Stupid.
Okay. So, positron, totally fine, right? Maybe a little bit dated sounding, but I did notice, was in this group of the other class that had the accelerator that was called it's called like the Toronto-Ramatic or something like that. There you go. It's like the 2009. It's 2017.
We didn't name it.
So electron positron, So that's it. Everything else gets a very sensible name because this was done before 1960. And so everything else gets named anti-something else. Much nicer name. For example, this guy is a muon. Over here, you have the antiparticles mu plus, and that is anti-muon. Okay, so everything except the positron follows those rules. That's nice. Okay. Now, not everything has charge, so you need another way to distinguish between these. Okay? So, if you look up at the subatomic particles, they're classified as, if you see over on the side, leptons and quarks. And, you know, if you can't see that far, I mean, if you can't see that far, you should be able to. Wear glasses. All right. You should then.
I'm legally
If you can't see that from here, you should get glasses. Just saying.
What if you already have
It's not that far. Okay. So you can see the muon has a negative charge, right? So those first three, the first six up there are leptons, right? The three of them are charged leptons, electron, muon, and then there's the tau, which follows the same rules, right? Now, the other three are neutrinos. You see electron, neutrino, muon, neutrino, tau, neutrino. Those have no charge, and you can see, wait a minute, they have antiparticles, and the answer is yes. So, if you have an electron neutrino, that's the symbol, that's the Greek letter nu. Nu for neutrino, see? It's kind of a pun because nu is the equivalent of the Greek letter N. So they call it this, but it's short for neutrino. Okay, and then it's just a subscript that induces the electron neutrino. The antiparticle of that, to indicate that, we write a bar above it. Okay, the bar above the particle means it's an antiparticle. So this is called the electron antineutrino. Okay? So, no big deal, you put bars above things. Okay. Next, the quarks. For whatever reason, we never write charges on the quarks, even though they're charged. See, there's 6 quarks listed over there. They have the stupidest names. You can tell then by when they were named. Those are the names. Down, up, strange, charm, bottom, and top.
I feel like strange and charm are...
Yeah, right? Because one is the opposite of down, and bottom is the opposite of top, and strange is what? And then,
Don't go into strange right now. Trust me.
Today, so
I know what it goes into.
Or some other time. But for those, we never put, for example, the up quark, we just put U. We don't put charge on it. There's actually a reason for it, but part of it is the charges are fractional. We don't want to deal with fractions. So we just put U for the up quarks. This is the up. Therefore, the antiparticle is, how do we write it? Yeah, we just put U bar. Right? We pronounce that U bar. So you put a bar over it, and this is the anti-up, which is not the same as down. That would be ridiculous. No, anti-up, not down. Okay, down, of course, is an anti-down that goes with it, which is not the same as up. Stupid names, stupid names.
So wait, you're saying up isn't up and down?
Well,
isn't
up
down.
is up, anti-up is not the same as down. That's what I said. I know, right? No, it's not on my flow, it's just a stupid name. Okay, so that's all the quarks. The bosons here, you don't really need to worry about. Bosons are basically all their own antiparticle, so they don't really have antiparticles to speak of. But when you get to the baryons, okay? The baryons are made up of quarks. You can see right here the quark content for each one. It tells you what it's made of, what quarks are made of. So, the way baryons work is you take, let's pick one of those up there. I'll explain. Come on, take a more interesting one.
Delta.
A. That's not a lambda.
No, please.
That's lambda.
Please don't do delta.
Sigma plus. Okay, this is sigma plus.
Delta.
You gotta learn a little bit. That's the lambda, the thing like that. That's called the capital lambda. This is the sigma. The thing that looks like 3 lines, like the Chinese letter sign.
The energy content of
Greek
a
letter
delta
C.
is insane.
It's pronounced C. It's a pain to say. C, yes. Becomes the modern X. Doesn't look like it, but it does.
Can't we just like
Okay,
that?
the sigma plus, right, is antiparticle because, so the sigma plus is a quark content of UUS. Okay, the antiparticle of the sigma plus would have a quark content of U bar, S bar. Right? Make sense?
Yeah.
As a result, you have to be able to distinguish, because this is 3 quarks and this is 3 antiquarks, they're not the same as each other. So you need to do 2 things. You need to put a bar above it to indicate that it's an antiparticle, because because it's different. And what's the charge of this thing going to be?
Negative.
Negative, so you put a minus on it. So the sigma bar minus is the antiparticle of the sigma plus. As opposed to if you have the sigma minus, which is a different particle, right? That's a DDS, right? That one's antiparticle would be what? Sigma bar plus, which is made of d bar, s bar. Okay? It's not that hard. You just have to remember the charge that you write here is the actual charge of the particle, always. Okay? Benji.
Never mind.
Okay, easy. Okay, good.
Thank you.
Flat. Time flat. Okay, good. Once you figure out how to name, and then the mesons, right? The mesons is the next stage. The mesons, a lot of them, so the mesons are made of, if you notice, are made of one quark, one antiquark. So you have one of these, like, if you're a good meson.
D0.
D0, all right. Actually, let's do the D plus first.
All right.
D plus, okay, is CD bar, okay? The antiparticle of that would have the quark content. You just reverse it, so it'd be C bar D. Make sense?
Oh, nice.
Right? Well, these are both mesons. They're both one quark, one antiquark. There's no way to tell. So because of that, we just write it as D minus, but we don't put a bar on it because he doesn't need one. Okay. Whereas these needed them to distinguish that from that, right? See, they're different. There's nothing. This is just another meson like the other. There's nothing different about it. So we leave it like that. Unfortunately, the neutrally charged ones, you don't have that option. So like the D0 is Cu bar. Its antiparticle is C bar U, but it has the same charge, right? So the neutral mesons, you have to put a bar over. If it sounds complicated, it's really not. Yes, there are simpler ways it could have been done, but it's really not that bad. You get used to it, I think.
Better than biology.
Yeah, that's basically what happens. Yeah. Okay, so let's talk about the rules, which are important. We can do this pretty fast. Here's the thing. With interactions, you so now we know the particles and you can know how to look them up. We'll talk about what they are later. Okay? But here's the thing. With chemistry, for example, you have certain reactions. And you don't talk about this a lot in chemistry, but I want you to consider the following reaction in chemistry.
How do we do this again?
Okay, what's the problem with this reaction?
It's chemistry.
What's the problem with this reaction?
It's chemistry.
It's not possible. It's not just not balanced.
Well, where's your
The
argon?
world is just not balanced.
Where's your...
Where the carbon and oxygen go, where the argon and chlorine come from, right?
Oh, no. Oh, no. We can't keep
Please don't.
So it's very
the oxygen.
Okay, so the problem with this is that it is not possible. Now, you don't spend much time in chemistry talking about reactions that are not possible, okay? But here we're going to, okay? We're going to look at, in fact, your homework assignment is just going to give you interactions like this, and you tell me, is it possible? And the way to figure out it's possible is by, now, it's not the same as balancing a chemical reaction, right? The rules are different. But just as in chemistry, some of them are possible, some of them are not. Some of them are possible but very unlikely. Some of them are just plain impossible. Right? Oh wait, 55. Okay, wait. I can't read a watch, sorry. So then there are 4 rules that you need to know. There are 4 tests, 4 things that have to be true. All 4 of them must be true for the reaction to be possible. Okay? And they're all conservation laws. What does conservation mean? Something must be the same before and after the interaction. So the first thing to look for is, 4 rules. Number 1 is, can you read this marker okay? Is it too light?
No, it's fine.
It's fine. First one is conservation of charge. Okay? So, let's do a bad example first. Let's say I have a proton and a neutron goes to an electron and a neutrino. Okay, so you look these up. P, you look up, it's a proton, it's one of the baryons. Okay? And it's a neutron. Notice that P doesn't have a plus after it, even though it should. Right? It doesn't. Because a proton, everyone knows what a proton is. And it's annoying because really it should have a plus after it, but it doesn't. So,
Why does a photon get listed then?
what? Photon is a gamma. Clever, right? Alright. So, proton, neutron goes, okay, now what you do is you check the charge. You take the total charge on each side. The proton has a charge of 1, so plus 1. Neutron, 0, so the total charge is 1. Now you check this side. The electron has a charge of negative 1. The antineutrino has a charge of 0, so you get minus 1. If these two are not the same, they are not, then no, impossible. Violates conservation of charge. Okay? On the other hand, here's one that does work. Okay? This is proton neutron goes to positron, electron neutrino. So, this is plus 1, this is 0. This is plus 1, this is 0. The sum on both sides is 1. This one passes the conservation of charge test. Passes all the other ones too as it happens. Okay? So, that's number 1. The next two work in a very similar way, which is great. So, number 2 is conservation of lepton number. Okay, lepton number means you go to this list here of leptons. Do you see it over on the side that says leptons? John, you have glasses? Right over on the side that says leptons, so that those first 6, those are the leptons. Okay? Here's how it works. Every lepton has a lepton number of 1. Every anti-lepton has a lepton number of negative 1. Everything else, such as quarks and so forth, has a lepton number of 0. It kind of makes sense, right? So lepton number is basically the number of leptons you have minus the number of anti-leptons you have. Okay, so let's see. Let's start with the bad one. Okay. This one also violates charge, so I'm think of it or whatever. Let's look at the lepton number right now. So what's the lepton number of the E minus? Is 1. E minus is an electron, which is a regular. So the negatively charged leptons are the leptons, the positively charged ones are the anti-leptons. A little bit annoying is Ben Franklin's fault, right? If electrons were positively charged, life would be much easier. However, he didn't know about electrons at the time, and so he had a 50-50 chance of getting it right, and he got wrong. So we're stuck with the negatively charged electrons. So this is a lepton number of 1. The neutrino has a lepton number of 1 also. So the total lepton number is 2. Over here, this is a what particle? This is an anti-muon because it's positively charged. So you have a lepton number of negative 1. This is a muon neutrino, which is a charge of 1. So the total lepton number is 0. These are not equal, so it's not possible. On the other hand, you have, if we do say, let's just do this.
E plus.
Let's do one that actually fits all equals. This one's fine. E minus has a sign of 1. An electron antineutrino has lepton number negative 1. Over here, mu minus is 1. Mu antineutrino is negative 1. So now it's a total of 0 on both sides, and that works. So far, so good? Okay. Next one is, I'll shorten this, is conservation of baryon number. Baryon number works about the same way, but look, we got a list of baryons. So if it's on this list, it's a baryon. How do you know if it's an anti-baryon? You remember? It's got a bar over it. It's got a bar over it, it's an anti-baryon. So they're pretty easy to recognize. You just look to see if they're on the list. So, for example, and it follows the same rules. So you might say baryon is 1, anti-baryon is negative 1, everything else is 0. So, for example, if we have something like, you know, there, good one. Okay, so this one conserves charge fine. Oh, it violates lepton number or whatever, I can fix that. There, now conserves lepton number 2. But if you count up the baryons, the proton is a baryon. So, here, let's take 4 5 there. The proton is a baryon, that's +1. The neutron is also a baryon, so that's another 1, right? Electron is not a baryon, which means 0, right? Okay, so the total on this side is 2. Over here, lambda naught, that's a baryon, it's up there, so +1. E plus, the baryon, that's +1. E minus bar is an anti-baryon, I put a bar above it. It's an anti-baryon, so that's -1. A neutrino is not a baryon at all, so that's 0. Add all these together and you get 1, so this one fails. Right? Okay, we're getting the hang of this? Right? A version of this that would work would just be something like, this, for example. Now we have 2 baryons on each side, so this baryon number on each side would be 2, and everything works. Yes? Yeah, so basically the exact same rules we apply to leptons. Okay, so this one works. Okay, the last one is a little bit more complicated. But you've actually already done the math for it, and that's conservation of energy. But the good news is, it's just a question of whether it's possible at all ever, right? So you don't know the energies of the particles. You're not doing a lot of calculation here, okay? Because you don't even know the energy particles. But there's a class of things that are just completely impossible in any reference frame with any amount of energy. And that is, okay, there are 2 types of interactions. We have decay interactions, and a decay interaction is a single particle going to some number of other particles. That's a decay. And then you have a scattering interaction. A scattering interaction is 2 particles going to some number of other particles. So the only thing that matters is the initial state. The initial state is 1 particle, it's a decay. The initial state is 2 particles, it's scattering. And the other initial state with 3 particles, not practically. It's hard enough to crash 2 particles together. So, right guys? So, so these are your 2 basic types. Okay, the rule for conservation of energy is 4 decays only. Okay, only 4 decays. So if it's scattering, this one's already done. You don't have to think about it. Okay? If there's 2 things in the initial state, then like, okay, we're already done. Right? You skip this rule. It's only if there's only 1 thing in the initial state you have to consider this. Why is this an issue? Because if you have only 1 thing in the initial state, right, it can have, of course, different amounts of energy depending on how hard you hit it. But you're always able to transform into what frame? Center mass frame, in which case, what's it doing? It's not moving at all, right? So, for a decay, when there's only 1 particle in the initial state, you can transform it into the reference frame where it's not moving. And then you can ask yourself, what particles can you make out of it, right? So can the electron decay into a proton? Right, well, the electron is a mass of 0.0005 GeV, the proton is about 1 GeV. Where would all that extra energy come from? Nowhere. Nowhere, because even you're like, no, I just give the electron a lot of energy, right? Well, sure, you can give the electron tons of energy relative to the Earth, but if you switch the electron's rest frame, all it's got is its mass. Okay, for that reason, you have this rule. So if you have a decay, A going to B, C, D, whatever, however many things, there could be any number of things in this final state. Then the mass of A must be greater than or equal to the mass of B plus the mass of C plus the mass of D, etc. Okay? The mass of the initial state must be greater than or equal to the sum of the mass of the final state. If it's not, it's energetically forbidden because you can go into that particle's rest frame and then all the energy it has is its mass, and then it doesn't have enough mass to create all these things. Why is that not a problem for scattering interactions? Well, because for scattering interactions, you have 2 particles. So there is no rest frame, right? One of the particles, at least, is always going to be moving. And because of that, you can make those two particles come at each other with crazy amounts of energy, right?
Yeah.
So, we have these two particles, you can have ridiculous amounts of energy, and thus there is no energy limit. In principle, it's possible. So you can have two electrons colliding to make two protons, no big deal, right? You just have to have enough energy. It's possible, right? But this one, with the single particle of the initial state, no matter what you do to it, it's not possible. And conservation of energy forbids it. Okay, so 4 laws, you check each of them. Remember that this one only applies to decay interactions. So like half the time, you can just be like, you can just ignore that one. Okay, so your homework, 10 problems, 10 interactions. You just check all the rules on each of them. Now, you can check more than one. You can violate more than one, so check them all, please. Okay, and then you tell me which ones it violates, or if it doesn't violate any, it happens. That's it, right? So this class is easy. All right. So you guys have a great weekend. Relax, enjoy it. Look, there's like nothing to do for ModPhys, right? Wow. So, see, I heard you guys were doing the exam when you did. So, right? Yeah, at least you can work on that.
Are you ready?
And